Hi guys, welcome back. In this section of videos we're going to start looking at actual force problems, and we're going to look at ways to deal with those problems, a general strategy for solving them. Each question is slightly different, so each question will have a different approach of how you are going to try and solve it, but there is a general set of guidelines, a general strategy that we can try and follow that's going to make your life a lot easier when we solve these problems. Okay, and you'll see I'm going to be following a very similar pattern throughout these questions, a very similar set of steps. And these steps are outlined here as follows. So, step number 1, decide which directions will be positive and negative. Okay, so you'll typically see me write out a little diagram somewhere in the corner of the picture that looks like this. Okay, and that's just me making me setting up a coordinate system. Okay, so we're saying up is positive and to the right is positive. Right, and that would mean that to the left and down would be the negative directions. Okay, we always need to define a positive and negative direction when dealing with vectors, especially forces, because when we start writing out net force equations, we're going to be either adding or subtracting forces depending whether they are a force pointing in a positive direction or a force pointing in a negative direction. So that's really important. You should always do that somewhere at the beginning of your problem before you write down any equations or anything. Okay, so that's step 1. Step 2, draw a diagram. So draw vector arrows from the object indicating direction of forces. And you'll see me draw something like this, where it'll be a dot representing the object. If there are multiple objects connected somehow, I might draw a dotted line, representing the connection, either a string or whatever, and another dot representing the second object. Okay, and then you can draw arrows sticking out of these dots representing the forces that the objects are experiencing. So let's say these two things are a car towing a trailer, and they're on a road. Okay, the car itself is experiencing gravitational force, which will signify with FGC for gravitational force for the car. And you will have a gravitational force for the trailer, call it FGT, gravitational force for trailer. Both of these are experiencing normal forces, which I'll call FN car and FN trailer. And depending on the situation, every diagram is going to be different. You're going to have different arrows sticking out of different objects. It all depends on the question. Okay, but you'll see a number of different questions we're going to answer. All right, this brings me to point number 3, treat connected objects as one. Okay, so in this picture here, we've said we've got a car towing a trailer. We can treat that as a complete system, okay, we say. So both of these objects are connected via the towing mechanism on the back of the car, the tow bar. And you can actually just treat this whole thing as one object with one mass, which would be the combined mass of the car and the trailer. And, if one object is connected to another, they're both going to be accelerating at the same rate. And we're going to analyze all the forces acting on all objects in that system. Okay. Again, we'll see how this all works later on when we answer a question. Okay, step 4, identify the velocities and or accelerations of the objects involved. So we need to have some idea of whether or not the objects are accelerating at all, or if they have no acceleration, because that will tell us whether there is a zero or a non-zero net force acting on our system of objects. Okay. So if this car and trailer were traveling at a constant velocity, say towards the right, we know that because it's a constant velocity, the acceleration would equal 0. Therefore, the net force acting on this system would be equal to 0 as well. And that comes from Newton's first and second laws. Okay. If the object was accelerating in some way, then the net force is not 0, and we'd have to analyze that a little bit more in depth, depending on the setup of the question. But again, we'll see a number of different questions. Step 5, identify the forces acting upon the object, leaving irrelevant forces out. So let's say that this car and trailer were accelerating, and they were accelerating that way, and I might just change that because typically we change the coordinate system so that the positive direction points in the direction of the acceleration. That makes things a lot easier for us. Okay, actually I'm going to add step 0. Set positive direction to be the same as direction of acceleration. Okay, so that is going to make things a whole lot easier if you just set that up to begin with. Okay, and that might mean rotating the way that you view the problem, and we'll see examples of that in a second. Anyway, where was I? Identify the forces acting upon the object, leaving irrelevant forces out. So we know that the net force, because the objects are accelerating towards the left, that means the net force must be towards the left. What that tells us is that there is no net vertical force. So we don't even really care what the vertical forces are, okay, because they're all going to cancel out anyway. So we can actually just ignore these normal forces and the gravitational forces and just look at the horizontal forces acting on this system, because we know in advance those vertical forces are going to cancel out. They're going to have no effect. So you might have some friction acting on the trailer, you might have some friction acting on the car, and the car is going to be using its engine to provide some kind of thrust force. So you really only have to analyze these 3 forces. You will also have some tension where the trailer is pulling back on the car, and you'll have some tension where the car is pulling back on the trailer. But notice that because they're connected using the same string, those 2 forces will be equal and they're pointing in opposite directions. They cancel each other out. So we can ignore tension if we're looking at the entire system. See that in a second. Step 6, resolve forces into components if necessary. So this really only becomes a problem if you've got things like inclined planes and stuff like that. If everything's sort of just horizontal or all vertical, you don't really have to worry about that. We'll see how to deal with that later on. Step 7, identify forces which may cancel each other out. So again, this really only comes into play when we have to resolve some forces into components, because when we identify which forces may cancel each other out, that really helps us to set up our net force equations. You'll see how that works in a second. And finally, step 8 is to start doing some maths. Set up your net force equation and solve for whatever particular quantity you need to solve for. Okay, so really all of this here, that is all done without maths. Okay, the only step that requires maths is this one. Okay, so this part here is physics. This part here is maths. If someone comes along and sets all this up for you and then gives you this final equation, you don't need to know anything about physics to be able to solve that final step. Okay, whereas if you didn't know physics, you wouldn't even be able to do all of that other stuff, steps 1 to 7. Okay, so that's our strategy. I'm going to see how this works for a few different kinds of questions. Here's question 1. A toddler drags his 4.5 kilogram cart of blocks across a floor at a constant speed. Underline, very important phrase. Constant speed of 0.75 meters per second. The force of friction between the cart and the floor is 5 newtons. And it is being pulled by a handle which is at an angle of 35 degrees above the horizontal. Calculate the force that the toddler exerts on the cart. So you'll notice I've written setup in the title of the slide. Setup is just us doing the first 7 steps from our strategy, and then after that we'll solve it. Okay. So here's our cart represented as a dot. Here's the floor. All right. Let's change color to start drawing some forces on this thing. Okay, so we've got a force being applied up that way. That is the force of the toddler's pull, and it's at an angle of 35 degrees. We've also got friction, and we're assuming that the object is moving this way. Okay, so let's write out a little coordinate system for ourselves. All right, but the fact that it says constant speed just means there's no net force, so that kind of becomes irrelevant, but doesn't really matter. There is a friction force pointing this way. We'll signify that with F, subscript F. Okay, that equals 5 newtons. All right, so we've identified the forces acting on the object. Now, again, there are still some other forces. There's still the gravitational force, and there's still the normal force. But in terms of this problem, we don't actually have to worry about them because it can all just be solved in terms of the horizontal forces. Okay, because there is no net force. It's moving at a constant speed. That means the net force in the vertical direction must be 0. And also the net force in the horizontal direction must be 0. So we can ignore them. We know that they're irrelevant to the problem. Okay, so really that's all we've got to worry about here. Okay, now one of our steps was resolve forces into components if necessary. So we're actually going to do that with this force that is pointing at an angle in reference to our coordinate system. So a dotted line is us splitting into a horizontal component, and also a dotted line splitting it into a vertical component. Now, we're ready to start writing a net force equation. And the way that we're going to write this is in the following way. We're going to say F net equals. And because most of the time we're only going to be looking at the net force in either the vertical or horizontal directions, that means we're going to be summing up or adding together the forces in either only the vertical or horizontal directions. In this case, we are going to only analyze this in terms of the horizontal forces, okay, which means this friction force and this component, horizontal component of the force the toddler is applying. So I'm going to write this little symbol here. If you've never seen this symbol before, it just means the sum of. It means I'm about to add all this stuff together. We're going to add all the forces in the horizontal direction, the x direction together. Okay. Now, what are the forces in the horizontal direction? Well, we've got a force in the positive horizontal direction. It is this horizontal component of the pulling force by the toddler. What is the size of this component? Well, here we need to do a little bit of trigonometry. That is going to be equal to the actual force that the toddler is pulling with times cos 35 degrees. Okay, if you don't know how I got that, go back and review your trigonometry. So that is a positive force, but we've also got a force pointing in the negative direction. We're going to subtract that. So that's why it's important for us to know which directions are positive and negative. So we're going to subtract the friction force, which we know is 5 newtons. And what do we know about the net force? We know that the net force has to be 0 because this cart is moving at a constant speed. So the sum of all the forces in the horizontal direction we know has to be 0 for it to be moving at a constant speed. Otherwise, if it wasn't 0, there'd be a non-zero net force and it'd be accelerating somehow. So I can make all of this stuff, the sum of all my horizontal forces, can make it equal to 0. Okay? And now we're ready to solve for the force that the toddler is pulling the cart with. Because really, we've got this equation here now. Okay? One equation with one unknown. Now, I've got a slide here where we can write out the answer, but I think we can fit it in here. So, therefore, the force that the toddler is applying to the cart is equal to 5 over cos 35 degrees. Just make sure 99.9, I think 100% of the time in physics, we're going to be dealing with degrees. So make sure your calculator's in degrees. Type all that in, we get 6.1 newtons, okay? And what that showed us is this force here, this force going up at an angle of 35, has to be 6.1 newtons in order for this cart to be traveling at a constant speed. Okay? So, that's our first question. Go back, review, try and see all the steps that we've applied to solve it. Okay? Most importantly is setting up your net force equation correctly. Okay? And also identifying the forces acting on the object and which forces may be irrelevant to our problem. Okay? So we'll stop there. We'll pick it up again from next time. Okay? See you then.